Welcome to the Deep Dive, where we plunge headfirst into a stack of fascinating sources, pulling out the most important nuggets of knowledge and insight to get you well-informed, fast. Today we're doing something, well, truly exciting. We're not just looking back at recent events, but taking a unique leap forward, diving into a snapshot of what could plausibly be happening, in the world of science, technology, and space just a few months from now.
That's right. It's fascinating stuff. The relentless march of scientific progress and innovation, it really never stops, does it?
Never.
This world of discovery is it's a constantly buzzing hive, always churning out breakthroughs that have the potential to shape our future in ways we might not even anticipate today. It's a current that's always flowing, always building.
Absolutely. And our mission for you today is a bit of a fresh take on that current. We're offering you a shortcut, really, to understanding the kinds of incredible advancements we can anticipate based on, well, the trajectories of current scientific research, anticipated mission timelines, and tech developments that are already well underway. Think of this as a plausible future history, specifically a deep dive into what a major scientific review from, say, May 2025 might look like. We'll use these hypothetical scenarios to truly grasp the significance and potential impact of these powerful trends.
And it's important to remember, our source material for this deep dive isn't some crystal ball, right? It's a comprehensive Sciencepect news special. And it's meticulously designed to extrapolate from the very real research and development happening right now.
Exactly.
It imagines what a typical monthly review of major scientific and technological news might sound like in the very near future. So it's less about making specific, nailed down predictions.
Yeah, not about being psychic.
Not at all.
Yeah.
It's more about exploring the undeniable trajectory of human ingenuity and discovery. It's about recognizing patterns, connecting dots, and really understanding the momentum of progress.
And why does this particular deep dive matter to you, our listener? Because honestly, it's your express lane to feeling genuinely well-informed about the leading edges of human endeavor without getting bogged down in all the information overload.
Right. We cut through the noise.
We aim to deliver those aha moments, those surprising facts, and that sense of connection to the rapid evolution of our world. So let's unearth some truly remarkable insights from this hypothetical May 2025 and prepare to be amazed by where we might be heading.
Sounds great. Where do we start?
Okay, let's launch into our first major section by doing what humanity has always done, looking up, way up into the cosmos. According to our Sciencepect review, May 2025 was reportedly a truly monumental month for humanity's renewed ambitions, returning to the moon, and also for our incredible ability to peer into the deepest, most mysterious parts of our universe.
Indeed. The foundational work being laid down today for future space exploration. It's setting the stage for some truly transformative leaps. Our May 2025 review highlights some critical hypothetical steps that bring those ambitious plans much closer to reality.
And first up, something really huge for NASA's Artemis program. A crucial step was reportedly taken in May 2025 with the Human Landing System, or HLS. Our sources indicate that a key HLS prototype, likely from a major commercial partner like, say, SpaceX or Blue Origin, successfully completed an uncrewed integrated test flight. Now, this wasn't just a simple test, was it? It simulated several absolutely critical phases of a lunar descent and ascent profile. What specific elements were they really putting through their paces, and why is this particular test so significant?
Well, the details emerging from this hypothetical May 2025 test are actually quite remarkable. It reportedly included the ignition and, importantly, the controlled firing of the landing engines in a vacuum environment.
Okay.
Now, that isn't trivial. Managing powerful thrust vectors precisely in the absence of an atmosphere is incredibly complex. I can imagine.
But beyond just firing the engines, the test also validated the precision guidance and navigation system performance, absolutely crucial for hitting a specific landing zone on the moon.
Right. You can't just land anywhere.
Exactly. They simulated propulsive braking, where the engines have to slow the vehicle down dramatically, and a controlled descent phase, potentially culminating in a simulated soft touchdown at a test site. This is a far cry from just a simple hop test. It's more like a full dress rehearsal for arguably the hardest part of lunar exploration.
I can only imagine the complexity. We're talking about operating these massive engines just meters above a dusty, airless surface, needing to navigate autonomously to a precise landing spot. What makes it so difficult compared to, say, landing on Mars, which at least has some atmosphere?
That's a really great question, and it highlights the unique challenges of lunar landings. On Mars, while it's certainly challenging, that thin atmosphere still provides some drag to help with deceleration, and you can use parachutes, at least partially.
On the moon, there's effectively no atmosphere. None. So every single bit of deceleration, every maneuver, has to be done purely with thrusters.
Wow.
This demands incredible fuel efficiency, incredibly precise throttle control, and really robust guidance algorithms to avoid obstacles like boulders or craters during that final descent. And then there's the dust.
Ah, the regolith problem.
Exactly. The exhaust plume itself can kick up massive amounts of lunar dust, or regolith, which can potentially obscure sensors or even damage sensitive equipment on the lander. So this May 2025 test, by reportedly validating these key propulsion, guidance, and structural integrity elements under realistic flight conditions, well, it represents a truly massive de-risking step for the entire Artemis architecture.
So let's connect the dots here. If this uncrewed test goes as well as our sources suggest it did in May 2025, what does that really mean for the Artemis program's goal of returning humans to the moon? How does it actually move the needle for us, the people watching this progress?
It significantly accelerates the timeline for potential crewed lunar missions. That's the bottom line. The human landing system is that absolutely crucial final piece of the puzzle that literally puts astronauts on the lunar surface. It's the difference between just orbiting the moon, which we've done before, and actually having boots on its surface again.
Right, the actual landing part.
Precisely. By tackling these monumental engineering challenges with an uncrewed integrated test like this, they validate the design, they refine the operational procedures, they gather invaluable data, all of which significantly reduces the risk for future crewed flights. It shifts the program from ambitious plans and theoretical designs towards tangible, verifiable progress. It firmly puts boots back on the moon later this decade within a clearer, more achievable sightline. It's frankly a huge confidence booster for the entire endeavor.
That is incredibly exciting. Okay, now shifting our gaze, let's go from our own celestial neighbor to distant, really exotic worlds. The James Webb Space Telescope, JWST, continues its just breathtaking mission of redefining our understanding of exoplanets.
It really does. Non-stop discoveries.
And our May 2025 Sciencepect review brought us new, truly astonishing data from a specific and frankly intriguing type of exoplanet known as a Hyson world. Now, I imagine many of our listeners might be wondering, what exactly is a Hyson world? That term might be new to some.
That's an excellent place to start because Hyson worlds really challenge our sort of preconceived notions of habitability. They're a theoretical class of planets, predicted to be larger than Earth, think super-Earths or mini-Neptunes.
Okay.
Potentially covered in vast, maybe even superheated oceans beneath incredibly thick, hydrogen-rich atmospheres. Imagine a gas giant like Jupiter or Saturn, but instead of just a core surrounded by gas, it has this deep global ocean underneath that thick atmosphere.
Whoa.
So the idea is that life, if it exists there, wouldn't necessarily be on a solid surface like Earth, but could potentially be within or beneath that extensive water layer, or perhaps even thriving in the lower reaches of the atmosphere itself.
Yeah.
It fundamentally broadens our search criteria for life beyond Earth, moving beyond just looking for, Earth 2.0.
That's a wild concept. And the atmospheric findings from JWST back in May 2025 were reportedly quite astonishing. Using its incredibly powerful spectrographs, astronomers detected multiple chemical signatures in the atmosphere of a particular Hyson candidate. Our source material mentions water vapor, methane, carbon dioxide, and intriguingly, other intriguing molecules. Now, while direct biosignatures, that sort of holy grail of confirmed life, weren't definitively reported, the findings were still incredibly compelling. What specifically made these findings so significant, even without that smoking gun biosignature?
The real breakthrough, I think, lies in the complex chemistry that was revealed. It wasn't just the presence of these molecules individually, like finding water vapor here or methane there. It was their precise ratios and how they were distributed within the atmosphere.
The context matters.
Exactly. Our sources highlight that these patterns align remarkably well with predictions for Hyson worlds that are theoretically capable of sustaining liquid water oceans, even despite the intense heat from their parent stars and those incredibly thick atmospheres. For instance, the relative abundance of water vapor and methane, coupled with the presence of carbon dioxide. That tells us a lot about the planet's internal processes and its atmospheric dynamics.
Interesting.
This kind of detailed data allows scientists to significantly refine their models of these planets, helping them better understand how they formed and evolved. So it's a huge step towards confirming if these Hyson worlds truly possess the necessary conditions for life as we might understand it. pushing the boundaries of what JWST can achieve. It's really not just about what you detect, but the whole chemical picture, the context of that detection.
So it's about building a more complete chemical fingerprint of these distant worlds, which then tells us much more about their potential for harboring life. That's a fascinating shift in perspective from just looking for a simple yes or no to life, isn't it?
It really is. It's about understanding the environment in much greater detail.
Okay, now let's pull back closer to home, but still a planet away. We turn our attention to one of the most ambitious robotic space missions ever conceived, the Mars Sample Return, or MSR, mission. Our Sciencepect review for May 2025 points to some significant diplomatic and technical progress, with an international agreement reportedly solidified between NASA and ESA. What does this actually mean for getting those precious Martian samples back to Earth?
Well, this mission, as you said, is incredibly ambitious. It's designed to bring rock and soil samples collected by the Perseverance rover currently on Mars all the way back to Earth.
What?
Why? For incredibly detailed analysis by instruments that are simply too large and complex to send to Mars.
Right.
Our sources highlight that throughout May 2025, following months of intense, really detailed discussions, reports confirmed a solidified international agreement and, importantly, an updated technical plan between NASA and the European Space Agency, ESA. This is absolutely crucial because it clearly establishes the key components and the precise roles of each agency in this incredibly complex multi-stage mission. It solidifies commitment and lays out a clear path forward.
So let's break down those key components. What exactly are NASA and ESA each committing to here based on this May 2025 agreement?
Okay, so the agreement reportedly included firm commitments on the development and launch timelines for the Sample Retrieval Lander, or SRL. That's primarily NASA's responsibility. This lander is a monumental piece of engineering itself because it has to carry the Mars Ascent Vehicle, the MAV.
The rocket off Mars.
Exactly. The rocket that will launch the collected samples from the Martian surface into Mars orbit. That's never been done before. Then on the ESA side, their commitment was solidified for the Earth Return Orbiter, or ERO, which they were developing. The ERO is the spacecraft that has the incredibly complex job of rendezvousing with and capturing that sample container in Mars orbit, and then ferrying those precious samples on the long journey back to Earth. It's like a perfectly choreographed dance across millions and millions of miles, requiring immense international cooperation.
This source also mentions that this May 2025 agreement reportedly addressed previous technical challenges and, crucially, funding uncertainties. What kind of hurdles are we talking about for a mission this complex, and how might this agreement have alleviated them?
Oh, the challenges for MSR are immense. It's arguably the most complex robotic space mission ever conceived, as we said. We're talking about ensuring the MAV can actually launch successfully from Mars's thin atmosphere and lower gravity, a totally unprecedented feat.
Right.
And then performing an autonomous rendezvous and capture in Mars orbit, which is also incredibly difficult, maybe even harder than landing. There have been ongoing concerns around the mass of the MAV, the complexity of the sample transfer mechanisms between the different spacecraft, and of course the substantial cost.
Understandable.
This May 2025 agreement, according to our sources, seems to have outlined specific, perhaps revised milestones and maybe adjusted launch windows that directly accounted for these technical demands and the funding realities. It demonstrates a shared international resolve to overcome these hurdles, essentially refining the blueprint to make it more robust and ultimately achievable.
And the scientific payoff for all this monumental effort, why is it so absolutely critical to bring these pristine Martian samples back to Earth rather than just analyzing them on Mars with rovers like Perseverance or Curiosity?
The scientific value is, quite frankly, immeasurable. While our rovers on Mars are incredibly capable, fantastic machines,
You are amazing.
bringing these pristine Martian rock and soil samples back to Earth allows scientists here to use instruments that are far more sophisticated, powerful, and diverse than anything that could ever realistically be miniaturized and sent all the way to Mars.
Right.
We're talking about huge laboratory equipment that can detect even trace biosignatures, determine precise isotopic ratios to understand planetary evolution, and conduct complex experiments over extended periods.
Things you just can't do remotely.
Exactly. It lets us answer fundamental questions about the planet's geological history, its past climate, its potential for past or even present life, and the processes that shaped it billions of years ago. It's literally like bringing a piece of Mars right into our most advanced labs on Earth. So the May 2025 agreement, by signaling this strong forward momentum, truly means we're getting closer to potentially unraveling some of the universe's biggest mysteries about life beyond Earth and planetary formation.
That really is a foundational mission. Okay, shifting gears now to commercial spaceflight and specifically heavy lift capabilities. SpaceX's Starship program continued its rapid development pace in May 2025. Following previous high-altitude and even orbital test flights, our sources indicated a successful test focused squarely on payload deployment mechanics. Now, while it may be less visually dramatic than a launch, I have a feeling this is far more significant than it might sound. What exactly did this test involve?
You're absolutely right to highlight the significance of this, even if it lacks, the fiery spectacle of a launch or landing. Our source material describes this May 2025 test as simulating the opening and closing of Starship's absolutely massive payload bay doors.
Right, the clamshell.
Exactly. And potentially deploying a simulated mass or a test article in a controlled environment, likely ground-based, perhaps in a vacuum chamber to simulate space conditions. This seemingly small detail is utterly fundamental to Starship's entire future utility and its potential role as a truly revolutionary transportation system.
And why is that specific capability simply opening and closing doors and deploying something such a vital engineering milestone?
Yeah.
It sounds almost mundane compared to reaching orbit.
Because Starship is designed to carry an unprecedented amount of cargo to orbit, to the moon, and eventually to Mars. But getting that cargo out once it's in space is just as critical as getting it there in the first place.
Good point.
Imagine building a giant moving truck, but having no way to open the back doors to unload the furniture. The ability to reliably open and close that enormous payload bay in the harsh vacuum and microgravity of space, to deploy satellites accurately, or to release large habitat components gently and with precision, it's absolutely non-negotiable for it to be a truly functional and revolutionary system.
Right.
This test reportedly gathered crucial data on the structural behavior of those huge doors, the complex mechanics of the deployment mechanism itself, how thermal extremes in space might affect them, and the intricate control systems required for precise controlled deployment. It's essential engineering validation.
So how does a successful test like this actually unlock new possibilities for Starship, moving beyond just carrying cargo to orbit? What kind of future missions does this help greenlight?
This test, if successful, as reported, significantly broadens the scope of what Starship can realistically do. Think about deploying massive satellite constellations, not just a few at a time, like we do now, but potentially hundreds in a single launch.
Wow.
Or delivering entire prefabricated habitat components for lunar or Martian bases, where they need to be gently deployed and possibly assembled robotically. It also paves the way for future space telescopes far larger and more powerful than even the James Webb Space Telescope, which would likely need to be assembled in orbit from multiple Starship-delivered segments.
That's incredible.
So, a successful test here means that Starship isn't just a launch vehicle. It's potentially a versatile orbital platform capable of constructing and deploying the next generation of space infrastructure and scientific instruments. It's really the nuts and bolts, the practical engineering, that makes those truly colossal space dreams possible.
That's incredible, shifting from just getting there to actually doing things, building things once we arrive in space. Welcome back to our deep dive. We've spent some exhilarating time exploring the cosmos, from pivotal lunar landing tests to uncovering the atmospheric secrets of distant exoplanets. Now, let's descend back to Earth and dive into the equally cutting-edge technological advancements that reportedly emerged in May 2025, particularly in fields like artificial intelligence, quantum computing, and advanced battery technology. The pace of innovation down here is just as breathtaking, isn't it?
It truly is. Our source material from May 2025 vividly illustrates how quickly breakthroughs are occurring, pushing the very boundaries of what we thought possible, transforming industries, and impacting our daily lives in ways that were frankly science fiction just a few years ago.
First up in the tech sphere, a significant breakthrough in general AI reasoning was reportedly demonstrated in novel problem sets coming from some of the leading AI labs. Now, it's crucial to clarify for our listeners, this isn't full artificial general intelligence, or AGI, which would match human cognitive flexibility across all domains. That's still a way off.
Right, important distinction.
But our source indicates it's a crucial step forward. What exactly did these AI models achieve that makes this such a significant milestone, moving beyond just narrow AI?
The real breakthrough, according to our May 2025 sources, seems to be that these new models reportedly showed enhanced abilities to tackle novel, previously unseen problem sets. This is key. It means they weren't just trained on a massive data set to do one specific thing very well, like identifying cats in pictures or playing Go. Instead, they demonstrated an enhanced capability for abstract reasoning, for planning, and crucially, for learning how to approach new problems without extensive prior training specific to that exact problem. This moves significantly beyond what we typically call narrow AI, which excels at one specific task but often struggles to generalize its knowledge to new, unfamiliar situations.
So how are they doing this? What's the sort of secret sauce behind this enhanced generalization? Is it new architectures, new training methods?
It seems to be a combination. The preliminary papers and presentations highlighted in our source material for May 2025 apparently describe new neural network architectures and also innovative training methodologies. These allow the AI models to build far more sophisticated, sort of hierarchical internal representations of complex systems and relationships. Think of it less like memorizing facts and more like developing a deeper, more flexible understanding of underlying principles or concepts. The source provides a compelling example. An AI reportedly capable of solving challenging logistics problems that it had never been specifically trained on, or even generating plausible new scientific hypotheses in fields like material science with minimal fine-tuning. It's a huge leap from, say, an AI that can only play chess or only recognize faces. It hints at a more adaptable, perhaps even intuitive form of intelligence.
That is a truly fascinating development. If these AIs can generalize knowledge and skills across different domains like that, what are the broader implications? How might this transform industries or even the way we approach scientific discovery itself?
Oh, the implications are truly profound, potentially revolutionary. This work, while still likely experimental and probably very computationally intensive at this stage, it suggests a future where AI isn't just an assistant doing grunt work, but a genuine collaborator in discovery. Imagine an AI not just sifting through millions of existing scientific papers, but actually proposing entirely new experiments in quantum physics or drug design that human researchers hadn't even conceived of yet, then maybe running virtual simulations to test their initial validity.
That's incredible.
Or designing novel drug compounds from scratch, predicting their efficacy and potential side effects with astonishing accuracy, drastically accelerating the whole drug development pipeline. It impacts scientific discovery, complex system optimization across almost any industry you can think of, and even creative fields like architecture, music, and design.
But there are other considerations too, right?
Absolutely. What's equally important, and our source emphasizes this strongly, is the concurrent and robust discussion happening around transparency and safety protocols. As these systems become more capable and more integrated into critical infrastructure, think finance, healthcare, energy grids, ensuring we understand how they arrive at their conclusions, making them explainable, and building in robust safety mechanisms becomes absolutely paramount. We need to trust these systems.
Absolutely. The more powerful the tool, the more critical the ethical frameworks and the guardrails become. This reported breakthrough in AI reasoning certainly pushes that conversation right to the forefront. Okay, moving to the equally complex but potentially even more transformative field of quantum computing. May 2025 reportedly brought some truly exciting news regarding error correction. Now, for those unfamiliar, one of the biggest hurdles, maybe the biggest hurdle to building large-scale, fault-tolerant quantum computers is the extreme fragility of qubits.
Right.
Those fundamental units of quantum information, they're just incredibly susceptible to noise and errors from their environment. It's like trying to have a coherent thought during an earthquake, maybe.
That's a pretty good analogy, yeah. The quantum states are just so delicate. The breakthrough reported in May 2025 apparently involves a major international consortium pooling resources from leading academic institutions and private companies, announcing they had successfully demonstrated a new, more efficient quantum error correction, or QEC code.
Okay, QEC.
Yes. This code is reportedly capable of correcting errors across a larger number of these noisy physical qubits to produce a smaller number of stable, usable, logical qubits. The force highlights that they were able to maintain the quantum state of several logical qubits for a significantly longer duration and through more computational steps than previously possible. And crucially, they achieved this with what the source calls a substantially improved ratio of physical to logical qubits.
That phrase, substantially improved ratio of physical to logical qubits, sounds very technical but important. Could you unpack that for us? Why is that specific ratio such a critical detail for the future of quantum computing?
Absolutely. It's fundamental. Think of it this way. To create one stable, reliable, logical qubit, the kind you actually need to perform complex calculations without errors accumulating at it, you currently need a large number of physical qubits. These physical qubits are inherently noisy and prone to errors, as we said.
Right.
So if you need, let's say, 1,000 physical qubits just to make one stable logical qubit, scaling up to truly useful quantum computers that might require millions of logical qubits, well, it becomes incredibly difficult, prohibitively expensive, and physically unwieldy. Just think of the engineering challenge.
Yeah, that doesn't scale well.
Exactly. This reported breakthrough means they've found a way, using this new QEC code, to achieve that necessary stability with a much smaller overhead of physical qubits per logical qubit. Maybe it's hundreds instead of thousands, or even less eventually. This is fundamental because reliable, efficient error correction is the absolute cornerstone for scaling quantum computers to sizes large enough to tackle problems currently intractable for even the most powerful classical supercomputers we have today.
So we're talking about quantum computers that aren't just theoretical curiosities in labs, but ones that could actually become practical tools sooner rather than later. What kind of problems could these more stable, fault-tolerant quantum computers realistically begin to solve?
The potential applications are genuinely revolutionary across many fields. Imagine designing entirely new drug molecules from scratch, precisely simulating their interactions with target proteins in the body to accelerate pharmaceutical discovery by orders of magnitude. Forget trial and error. Or creating entirely new materials with custom designed properties like maybe eventually superconductors that work at room temperature, or incredibly efficient catalysts for chemical reactions needed in industry. Quantum computers are also predicted to excel at complex optimization problems, which could revolutionize logistics, financial modeling, supply chain management, or even things like traffic flow management in smart cities.
So many areas.
Right. While the noisy quantum computers we have today, with tens or maybe hundreds of qubits, are interesting research tools, achieving the thousands or even millions of fault-tolerant logical qubits needed for these big applications absolutely requires robust and efficient QEC. This reported milestone, even if it's still demonstrated at a relatively small laboratory scale, represents a monumental step on that critical path. It suggests that scaling to more useful quantum computation might be possible significantly sooner than some pessimistic predictions, bringing us closer to achieving genuine quantum advantage for specific, high-value problems.
This is genuinely moving quantum computing out of the realm of pure theory and closer towards real-world application, making future breakthroughs far more accessible and impactful. Very exciting. Okay, shifting now to a technology with perhaps more immediate consumer and industrial impact: battery technology. May 2025 saw truly promising developments, specifically in the realm of solid-state batteries. Now, these batteries famously use solid electrolytes instead of the liquid or gel electrolytes found in current lithium-ion batteries, and they promise a whole host of advantages. What are those key advantages that solid-state batteries promise, and why haven't they become widespread yet? There's been talk about them for years.
That's right, the hype has been around for a while, but the engineering is tough. The core promises of solid-state batteries are really compelling. Potentially greater energy density.
Meaning more power or range.
Exactly. More power or longer range for the same size and weight compared to current batteries. Also, significantly faster charging times. Enhanced safety is another big one, mainly because the solid electrolyte is generally non-flammable, unlike some liquid electrolytes.
That's a key benefit.
And potentially much longer lifespans, meaning more charge cycles before they degrade. However, the path to commercialization has been fraught with engineering challenges. Getting the solid electrolyte material to maintain good, consistent contact with the electrodes, especially as the battery charges and discharges and materials expand or contract slightly, has been very difficult. Poor contact leads to performance issues and rapid degradation.
Right.
Plus, manufacturing these materials at scale and keeping costs down has also been a significant hurdle. It's just hard to make them reliably and cheaply compared to mature lithium-ion tech.
And according to our source, May 2025 brought reports, particularly from companies focused on electric vehicles and portable electronics, indicating a significant breakthrough in both material science and the manufacturing processes needed. What were the specific results demonstrated in these prototypes that made this so exciting? What numbers are we talking about?
The reports indicated the creation of solid-state battery prototypes that demonstrated not just substantially higher energy density, meaning For instance, an electric vehicle could potentially travel significantly further on a single charge with a battery of the same physical weight.
Okay, that's big.
But also the truly game-changing ability, reportedly, to charge from near empty to about 80% capacity in under 10-15 minutes under controlled test conditions.
Under 15 minutes, wow.
Yeah, imagine plugging in your electric car during a quick coffee break, and by the time you're done, it's practically full. This isn't just a minor incremental improvement, it's a leap forward in the practical usability of electric vehicles and maybe even our portable electronics down the line.
That's a tangible impact on daily life right there. If these figures can actually be scaled up and produced economically, how might this redefine our transportation infrastructure or even the design of our cities?
Oh, the ripple effects would be enormous. For electric vehicles, that higher energy density directly translates to significantly longer range, which could completely alleviate the range anxiety that still holds some people back from buying EVs.
Definitely.
But the truly revolutionary aspect, I think, is that charging speed. It makes refueling an EV much more comparable in time to filling up a conventional gasoline tank. That could dramatically alter consumer perception and accelerate EV adoption even faster.
Makes sense.
It might also reduce the need for quite as much extensive public charging infrastructure that requires long dwell times, potentially shifting the focus more towards ultra-fast charging hubs, like highway service stations.
Yeah.
For cities, it could mean quieter, cleaner transportation fleets that are easier to manage. And for portable electronics, imagine devices that last days and then recharge fully in just minutes. Plus, the improved safety aspect, thanks to those non-flammable solid electrolytes, also reduces a significant concern associated with current battery tech. Now, obviously, mass production at low cost and ensuring long-term durability in real-world conditions remain significant challenges.
Always the catch.
But this reported May 2025 breakthrough suggests that widespread adoption of high-performance solid-state batteries could be much closer than previously thought. It's really about empowering widespread, efficient electrification across the board.
So we could genuinely be looking at a future where our phones charge almost instantly, and electric cars can go for hundreds and hundreds of miles and then refuel during a quick coffee break. That is a truly transformative upgrade for countless people. Okay, finally in this tech section, let's turn to the realm of biotechnology. May 2025 brought genuinely exciting news regarding the clinical application of gene editing technology. Now, CRISPR-Cas9, as many listeners know, has already revolutionized genetic research in labs worldwide. And the focus has increasingly been shifting towards using it as an actual therapeutic tool. While ex vivo therapies, where you take cells out of the body, edit them in the lab, and then put them back in, have shown some promise, delivering CRISPR directly into the body or in vivo to edit cells right where they are needed has been a major, major challenge. Why is this in vivo delivery so much harder?
The challenge with in vivo delivery is, well, it's akin to trying to perform microscopic surgery on specific cells scattered throughout the body without affecting any other cells.
Yeah, that sounds tricky.
You need to get the CRISPR machinery, essentially, the molecular scissors, the Cas9 enzyme, and its guide RNA telling it where to cut precisely to the target cells within the incredibly complex environment of the human body. You need to do it safely, effectively, without causing unintended edits elsewhere in the genome, off-target effects, without triggering a harmful immune response against the delivery vehicle or the CRISPR components themselves. It's an incredibly intricate delivery problem.
Makes sense.
Our source highlights that in May 2025, a research team, likely collaborating with a biotech company, announced the first reportedly positive Phase 2 clinical trial results for an in vivo CRISPR-based therapy. This was reportedly targeting a specific genetic disorder. The source mentioned possibilities like a form of inherited blindness, or perhaps a particular metabolic disorder, or maybe a neurological condition caused by a known single gene defect.
And the results, which were apparently presented at a major medical conference, were reportedly very encouraging. The therapy was not only safe and well tolerated by the patients in the trial, but it also showed statistically significant improvement in clinical endpoints related to the disease compared to a control group. That sounds like, well, a monumental step forward for in vivo gene editing, doesn't it?
It absolutely is. Monumental is the right word. What makes this so incredibly significant is that demonstrating safety and efficacy for an in vivo CRISPR therapy in a Phase 2 trial, which involves a larger group of patients than the initial Phase 1 safety trials, provides really strong evidence that this direct in-body gene editing approach can actually work to correct genetic errors in situ.
Right, inside the patient.
Exactly.
Yeah.
Overcoming that massive delivery challenge and then showing a clear, measurable therapeutic effect opens the door wide for potentially treating a much broader range of genetic diseases directly at their source, rather than being limited to conditions where you can easily extract, modify, and reintroduce cells, the ex vivo approach. This could include systemic diseases that affect many organs throughout the body, or conditions where ex vivo treatment is simply not feasible or practical.
So what does this all mean for patients and for the future of medicine? What kind of hope does this offer, realistically?
Well, obviously, further trials, larger phase 3 trials, and subsequent regulatory review and approval are still necessary before any such therapy becomes widely available. That's important to stress.
Sure, the process takes time.
But these kinds of positive phase 2 results offer immense hope for patients suffering from previously untreatable or poorly managed genetic conditions. For many, this could represent the first time they've had a truly effective therapeutic option on the horizon that addresses the root cause of their disease. It fundamentally validates in vivo gene editing as a powerful future therapeutic modality, promising to potentially change the prognosis for millions of people globally. Imagine a future where a single targeted treatment could correct the underlying genetic flaw, causing devastating conditions like Huntington's disease, certain types of muscular dystrophy, cystic fibrosis, sickle cell anemia. The list goes on.
That's incredible potential.
It's about getting ahead of these devastating diseases, repairing the root cause at the genetic level, and giving patients and their families genuine, tangible hope, where perhaps there once was very little. This is truly translational science, making that critical leap from the lab bench to the patient's bedside.
Welcome back to the deep dive. We've journeyed through the cosmos and explored cutting-edge technological advancements that could redefine our daily lives. Now, let's broaden our scope further and delve into the fundamental scientific discoveries and advancements from May 2025, spanning physics, chemistry, biology, and earth science. These breakthroughs often lay the groundwork for future technological revolutions, pushing the very boundaries of our understanding of the universe itself.
Indeed. These are the insights that fill in the fundamental puzzles of how our universe works, from the tiniest subatomic particles to the largest planetary systems and Earth's own complex dynamics. The pursuit of this core knowledge continues to yield incredible insights and potential game changers for humanity.
Okay, first up, something with enormous potential impact. For decades, controlled nuclear fusion harnessing the process that powers the sun has been seen as the ultimate potential source of clean, virtually limitless energy here on Earth, while massive international projects like ITER continue to progress steadily.
If slowly.
If slowly, yes. A burgeoning private sector fusion industry has been developing innovative, often faster-paced, and sometimes quite different approaches. Our May 2025 Sciencepect review highlighted that a leading private fusion company reportedly announced a truly significant achievement in their reactor development. What exactly was this breakthrough, and why is it such a big deal for the future of energy?
The real breakthrough here, according to our sources, was the reported demonstration of sustained net energy gain for a measurable period. Now, this is crucial. It means the fusion reaction didn't just break even on the energy put into the plasma itself to heat it up to millions of degrees.
Right, the Q plasma measure.
Exactly. It reportedly produced more energy than was required to initiate and sustain the entire system. This calculation supposedly includes the energy needed for the powerful magnets, the complex heating systems, the vacuum pumps, control systems, essentially, everything needed to make the whole device run. This potentially goes beyond previous break-even points often cited in the field, which might only refer to the energy balance within the plasma itself, not the whole wall plug efficiency.
Okay, that's a key difference.
And the source suggests this company might be using a different confinement method than the traditional large donut-shaped tokamak reactors like ITER. Perhaps they're using a stellarator design, or maybe an inertial confinement approach, or even magnetic targets. It shows the diversity of innovative approaches currently being pursued in the private sector.
So, for the listener, what does sustained net energy gain accounting for the whole system mean in practical terms for the timeline of commercial fusion power? Is this the moment we've all been waiting for? The fusion dream realized?
Well, let's manage expectations slightly. While the scale of this specific demonstration was likely still modest compared to what a future commercial power plant would need, think maybe kilowatts or perhaps megawatts of net power, not the gigawatts needed for the grid.
Okay.
Achieving this level of sustained net gain for the whole system in a private sector setting marks a critical validation of their specific technological approach and the underlying physics they're using. It demonstrates, perhaps for the first time, convincingly outside government labs, that their conceptual design can actually generate more energy than it consumes reliably over a period of time.
That's still huge.
It is huge. It signals that commercial fusion power, long considered decades away, might genuinely be accelerated by diverse and rapid innovation happening outside of the large, sometimes slower-moving, government-led consortia. It definitely boosts investor confidence, helps attract more top talent to the field, and intensifies the competitive drive among these private companies to be the first to truly harness this power commercially. The specific details of the achievement, of course, including the precise energy gain factor, often called the Q total or Q engineering factor for the system, and the exact duration the net gain was sustained, will be key metrics that researchers globally will scrutinize intensely once published. But it undoubtedly shifts the conversation significantly from if practical fusion is possible towards when and how it will be achieved.
That would be a genuine game changer for global energy needs. Truly a monumental step towards a cleaner, more sustainable energy future. Okay, next up, superconductivity. This is the amazing ability of certain materials to conduct electricity with absolutely zero resistance, which holds the promise of truly revolutionary technologies. Think lossless power grids saving enormous amounts of energy, incredibly fast electronics, and the powerful magnetic fields needed for things like MRI machines and particle accelerators. However, the big catch is that current superconductors typically require cooling to extremely low, often very expensive, temperatures using things like liquid helium. The holy grail in physics and materials science for decades has been finding materials that superconduct at higher temperatures, ideally even room temperature.
The ultimate dream, yes. And this May 2025, our source reported that a research team published truly intriguing findings on a new material candidate, a specific compound exhibiting superconductivity at a significantly higher temperature than previously confirmed ambient pressure superconductors. Now, it likely still requires some level of cooling, let's be clear.
Not room temperature yet, then.
Probably not, no. But what's fascinating is the reported temperature range where superconductivity was observed. It supposedly approached, or perhaps even exceeded, -70 or -50 degrees Celsius. That's roughly -94 to -58 Fahrenheit at ambient or relatively low pressure. This is a significant step up. The material itself was described as potentially a novel hydride compound, or perhaps a specially engineered ceramic or even an organic structure. It reportedly showed the characteristic signs of superconductivity, like the Meissner effect where it expels magnetic fields, and of course zero electrical resistance below that critical temperature.
So while it's not yet the dream of room temperature superconductivity that would change everything overnight, why is pushing the temperature boundary up by even, say, 20 or 30 degrees Celsius like this still considered such crucial progress? How does this make potential applications more feasible?
Because each incremental increase in the superconducting transition temperature, TCC, means significantly less energy is required for cooling, and potentially simpler, cheaper refrigeration systems can be used. For example, if a material can reliably superconduct above the boiling point of liquid nitrogen, which is -196 Celsius or 77 Kelvin.
Right, much cheaper than helium.
Exactly. That opens up a far wider range of practical applications because liquid nitrogen is relatively inexpensive and much easier to handle compared to liquid helium, which is required for many current low-temperature superconductors. Pushing it up towards -50 or -70 degrees Celsius, as this new candidate reportedly does, means you might eventually be able to use more readily available commercial-grade refrigeration techniques, perhaps even multi-stage coolers without cryogenic liquids. This makes potential applications like building truly lossless power transmission grids more economically viable, or enables more powerful, compact, and energy-efficient magnets for things like medical imaging, MRI, scientific research, or maybe even future magnetic levitation transport.
Okay, I see.
It's a slow but steady march towards a potential technological revolution where superconductivity could permeate many aspects of our technological lives. Every degree counts.
That's compelling. It highlights that it's not always just about the absolute breakthrough, but the consistent incremental gains that really make the difference in practicality. And like all such high temperature claims in this field, which has seen some controversies,
Indeed.
I assume independent verification by other labs will be absolutely critical and probably already underway.
Precisely. The discovery reportedly involves sophisticated material synthesis techniques and very rigorous measurement protocols to rule out artifacts. But in the challenging world of high-temperature superconductivity research, Independent verification and reproduction of the results by other credible research groups is absolutely essential before the claim is widely accepted by the scientific community. That rigorous process will undoubtedly be well underway following a May 2025 announcement like this. Nevertheless, identifying promising new candidate materials, even if they need further verification, is a vital step in the long and difficult journey towards harnessing the truly transformative power of high-temperature superconductivity. What's compelling is that it shows ongoing, rigorous innovation is still happening in this challenging field.
And even those incremental gains in raising the temperature could have massive ramifications down the line for our energy infrastructure and computing power. Fascinating stuff. Okay, moving now to a field that impacts literally all of us, climate science. The ongoing challenge of climate change requires ever more accurate modeling to predict future impacts and, crucially, to inform effective mitigation and adaptation strategies. Our May 2025 Sciencepect review reportedly saw the release of updated analyses and refined climate models incorporating crucial new data on complex climate feedback loops. What exactly are these feedback loops, and what kind of new data are scientists integrating into the models?
Climate feedback loops are natural processes within the Earth system, where an initial warming or cooling trend triggers further changes that either amplify positive feedback or dampen negative feedback, the original trend. They're absolutely critical to understanding the true pace and ultimate scale of climate change, because they can significantly alter the planet's sensitivity to greenhouse gas emissions. Our May 2025 source highlights that researchers presented updated models incorporating more detailed, real-world observational data on several specific important feedback loops. For instance, they reportedly included enhanced data on permafrost thaw rates in the Arctic and subarctic regions, and better estimates of the associated methane and CO2 release, methane being a particularly potent greenhouse gas.
Right, the thawing tundra problem.
Exactly. They also integrated new understanding, derived from satellite and ground data, of how changes in cloud cover both the amount and type of clouds affect the Earth's reflectivity, albedo, as the planet warms. Clouds are notoriously complex to model, and they incorporated refined data on observed shifts in major ocean current patterns, like the Atlantic Meridional Overturning Circulation, AMOC, which play a huge role in distributing heat around the globe. This new data was apparently collected over recent years from a combination of advanced satellites, extensive ground-based sensor networks, and deep oceanographic surveys using floats and ships. It provides a far more nuanced and data-driven picture of these complex processes than was previously possible just a decade ago.
So how do these refinements, integrating all this new observational data on feedback loops, actually change our understanding of projected warming trajectories? Does it give us a clearer, or perhaps, as the source hinted, a more concerning picture of the future?
The refined models reportedly provided, as you said, a clearer, albeit potentially more concerning, picture of projected warming trajectories under various future greenhouse gas emissions scenarios. By better accounting for the strength of some of these positive feedback loops processes, where initial warming triggers further warming, creating a kind of snowball effect, the models reportedly indicated that reaching or exceeding critical global temperature thresholds, like 1.5 or 2 degrees Celsius above pre-industrial levels, might occur slightly sooner than previously modeled, especially under higher emission pathways. Or, alternatively, the results might suggest that the upper bounds of warming projections, the sort of worst-case scenarios, were perhaps more likely under high-emission pathways than earlier models had indicated. Essentially, it suggests that Earth's natural systems might amplify human-caused warming in ways, and perhaps at speeds, we've only just begun to fully quantify with high confidence.
So this continuous refinement of climate models based on the latest real-world data is obviously not just an academic exercise. It's essential for understanding our planet's future trajectory. What's the broader relevance of these updated models for policymakers and for us, the public? How should we interpret this?
It is absolutely essential work. This kind of continuous model refinement, rigorously grounded in the best available real-world observations, is the bedrock of climate science. It allows policymakers, businesses, and scientists to have a more accurate understanding of the risks we collectively face under different future scenarios. And crucially, it underscores the urgency required to transition rapidly towards a sustainable, low-carbon future to avoid the worst impacts.
Right, it informs action.
Exactly. If we connect this to the bigger picture, the May 2025 reports really underscored the profound interconnectedness of Earth's systems. It shows vividly how seemingly localized changes, like permafrost thaw happening primarily in the Arctic, can have significant global ramifications through these complex feedback loops affecting weather patterns and sea levels worldwide. It reinforces the existing scientific consensus on human-caused climate change, but does so with ever-increasing precision and detail. It gives us better tools to make informed decisions about both mitigating emissions and adapting to the climate changes that are already unavoidable. It's a stark reminder that our planet is a complex, interconnected system, and understanding those intricate connections is absolutely key to addressing the climate challenge effectively.
That truly emphasizes the intricate dance of our planet's systems and the need for robust science to guide us. Finally, in the realm of medical science, truly promising developments were reported in May 2025 regarding the early diagnosis of complex neurodegenerative diseases, conditions like Alzheimer's and Parkinson's disease. For patients and their families, as we all know, early diagnosis is absolutely crucial for accessing support and, importantly, for the potential effectiveness of future treatments, which are likely to be most beneficial before significant irreversible neuronal damage occurs. What novel techniques were highlighted in these reports from May 2025?
The source highlights progress on really a dual approach in May 2025. Significant advancements in developing novel biomarkers found in body fluids, and also improvements in diagnostic imaging techniques, often boosted by AI.
Okay, biomarkers first.
Right. One very promising avenue involved the development and rigorous testing of sophisticated blood tests, or perhaps spinal fluid analysis. These tests are reportedly becoming capable of detecting specific protein aggregates like misfolded amyloid or tau proteins for Alzheimer's or other biochemical markers. Think of them as subtle chemical footprints of the disease process in the very early stages, potentially years, maybe even a decade or more, before the onset of any significant cognitive or motor symptoms.
Years before. That's incredible.
It really is. This
Wow.
leverages incredibly advanced technologies like highly sensitive mass spectrometry or new types of immunoassays, which can pick up these incredibly faint molecular signals that were previously undetectable.
And the other promising area mentioned was imaging. How are techniques like MRI or PE scans evolving to help with earlier diagnosis?
On the imaging front, there's been reported progress in advanced techniques, possibly combining things like functional MRI, fMRI, which looks at brain activity, with specialized PT scans. These PT scans use tracers specifically designed to bind to and visualize those pathological proteins we just mentioned, like amyloid plaques or tau tangles, directly in the living brain.
So you can actually see the disease pathology.
Exactly. And the key development here is often combining this advanced imaging data with sophisticated AI analysis. Machine learning algorithms are getting much better at analyzing these complex scan images to identify very subtle changes in brain structure, connectivity, or function that might be indicative of early-stage disease, perhaps even before the brain shows obvious signs of atrophy or damage visible to the human eye alone. So yes, it's really becoming a multi-pronged attack on early diagnosis, combining chemical insights from biomarkers with structural and functional insights from imaging, all enhanced by AI.
That's a truly powerful combination. What kind of results were being reported from these early diagnostic methods in May 2025, according to the source? And what hope do they realistically offer for patients and families dealing with these devastating diseases?
The results reported in May 2025, likely from ongoing longitudinal studies or specific clinical validation trials, were reportedly very encouraging. They apparently showed high sensitivity and specificity for these new tests. Now, in simple terms, high sensitivity means the tests are good at correctly identifying individuals who do have the early stages of the disease, minimizing false negatives. High specificity means they are also good at correctly identifying individuals who do not have the disease, minimizing false positives.
Both are crucial.
Absolutely. Some reports might have also highlighted the ability of these combined methods to differentiate more accurately between different types of dementia, like Alzheimer's versus frontotemporal dementia, for example, which is critical for prognosis and potential future targeted treatment strategies. While many of these techniques are likely still largely in clinical validation phases and not yet in widespread routine use,
Sure.
if we connect this to the bigger picture, these advancements offer immense hope for a future where neurodegenerative diseases can be identified much, much earlier, perhaps even in a preclinical stage. This would be revolutionary because it opens a critical window for potential interventions once effective disease-modifying treatments become available, which is another major area of research that could potentially slow or maybe even halt the progression of the disease before it causes widespread devastation. It could fundamentally change the prognosis for millions of patients worldwide. It's really about giving patients and their families genuine hope and the possibility of proactive intervention rather than just reactive management after significant damage is already done.
It's about getting ahead of these devastating diseases, offering tangible hope where there once was very little, an incredibly important area of progress. And that brings us to the end of our deep dive into the incredible science, technology, and space news from this hypothetical but plausible May 2025. What an exhilarating ride it's been, hasn't it?
It really has.
From humanity's bold ambitions to return to the moon and unravel the mysteries of distant Hyson worlds, to pushing the very boundaries of artificial intelligence, quantum computing, and sustainable fusion energy, and making truly significant strides in medicine with CRISPR and early disease diagnosis, plus fundamental physics like superconductivity. It's just crystal clear that the pursuit of knowledge and innovation continues at a truly breathtaking pace across every frontier of human understanding.
And each of these potential advancements we discussed, which are really extrapolations from the incredible work being done today by researchers and engineers worldwide, represents countless hours of dedicated research, ingenious engineering, failures, successes, and collaborative effort across the globe.
Absolutely.
They serve as a powerful reminder of humanity's enduring curiosity, our relentless drive to solve incredibly hard problems, and our profound capacity to understand and even begin to shape the universe around us, from the quantum level to the cosmic scale. It's really a testament to what we can achieve when we focus our collective ingenuity on these big challenges.
And this deep dive, while speculative in its specific May 2025 details and dates, is intended as a way for you, our listener, to stay ahead of the curve, to understand the crucial foundational work happening right now that will undoubtedly shape tomorrow. It's about recognizing these powerful trajectories of innovation and beginning to consider how they will inevitably impact your lives, your communities, and our world at large in the coming years and decades.
And maybe, as we consider these incredible hypothetical breakthroughs, from the almost limitless promise of fusion power to the ability to perhaps diagnose devastating diseases, years before they manifest, a profound question emerges for all of us to think about. What responsibility do we bear as individuals and as a society to thoughtfully guide these powerful new technologies as they emerge? How do we ensure that these advancements are developed and applied ethically, equitably, in a way that truly benefits all of humanity, not just a select few? And what ethical guardrails, what societal conversations must we collectively establish now as the pace of discovery only seems to quicken? It's a critical, ongoing conversation for us all to ponder as we step further into this increasingly complex and technologically advanced future.
That's a powerful thought to leave everyone with. Until next time on The Deep Dive, keep exploring, keep questioning, and keep looking up.